MSAN, a multi-service access node, MSAN, is a versatile telecommunications device that acts as a bridge between the customer's premises and the core network. It is a critical component in the evolution toward next-generation networks, NGN. Definition: an MSAN is a single platform installed in a telephone exchange or a roadside cabinet. It aggregates various types of customer traffic such as traditional voice, POTS, broadband data, DSL, and fiber-based services and converts them into a unified digital format, typically IP, Internet Protocol, or ATM, to be transported over the core network. Why it was introduced before MSANs: service providers had to maintain separate, siloed equipment for every service. POTS, voice, required TDM switches. Broadband required DSLAMs. ISDN required its own dedicated infrastructure. The shift to MSAN was driven by convergence, the industry-wide move toward all IP networks. Cost efficiency, reducing the physical footprint, power consumption, and maintenance costs of multiple machines. Flexibility, allowing operators to provide different services, voice plus data, to a customer simply by swapping a line card rather than building a new network. Key function: signal conversion, converts analog voice, POTS, into digital packets, VoIP, and vice versa. Traffic aggregation, collects data from thousands of subscriber lines and multiplexes it into high-speed fiber uplinks. Service integration, supports legacy services, like fax and ISDN, alongside high-speed VDSL2 or G.fast point 10 line testing, built-in diagnostic tools to check the health of the copper or fiber loop without sending a technician. Comparison: MSAN versus DSLAM. While a DSLAM is a precursor to an MSAN, they differ significantly in scope. DSLAM, digital subscriber line. MSAN, multi-service access feature access multiplexer, node, primary goal: provides only broadband, data. Provides voice, data, and video. Voice needs a separate splitter and a voice integrated, handles voice natively, support switch. VoIP/SIP. Network designed specifically for NGN, IP usually connects to an ATM or IP core. Core-based, cores. Modular, supports DSL, POTS, versatility limited to DSL technology. ISDN, and fiber. MSAN architecture. The architecture of an MSAN is modular and designed for high availability, chassis/shelf, the physical frame that houses all components. Control/switching unit, the brain that routes traffic and manages the node. It usually has a redundant pair for high availability. Line cards, these vary based on the service. POTS cards, for traditional analog phones. DSL cards, for ADSL2+, VDSL2, or SHDSL. Combo cards, can provide both voice and data on a single port. Optical cards, for FTTH, GPON/EPON, services. Uplink interface, high-speed ports, 10 GE or 100 GE, that connect the MSAN to the core ISP network. Power and cooling, rectifiers to convert AC to -48 VDC and fan units for thermal management. Available vendors. Most major telecommunications infrastructure providers offer MSAN solutions. Huawei, example Smart AXMA 5600T series, the most widely deployed globally. Nokia, formerly Alcatel-Lucent, example ISAM 7302. ZTE, example ZXA10 series. Fujitsu, example GeoStream Access Gateway. Adtran, known for modular and outdoor optimized MSANs. Zyxel, offers compact MSANs for smaller deployments or enterprise use. Modulation schemes in xDSL. Modulation in xDSL, digital subscriber line, is the process of mapping digital data onto electrical signals so they can travel over copper telephone wires. Because copper wires were originally designed only for low-frequency voice, 0 to 4 kHz, xDSL uses high-frequency bands and sophisticated modulation to squeeze high-speed data into that same wire. The industry has evolved from simple single-carrier methods to the complex multi-carrier systems used today. Discrete multitone, DMT. DMT is the industry standard for almost all modern DSL variants, ADSL, ADSL2+, VDSL2, and G.fast. It is a form of orthogonal frequency division multiplexing, OFDM, tailored for copper wires. How it works: DMT divides the available frequency spectrum into many small, independent subchannels called bins or tones. In ADSL, each bin is 4.3125 kHz wide. There are typically 256 bins in ADSL and up to 4096 bins in VDSL2. Adaptive loading, this is the killer feature of DMT. The modem tests each bin individually. If a specific frequency has too much noise, example from a nearby AM radio station, the modem reduces the number of bits sent on that bin or shuts it off entirely, shifting the data to cleaner bins. Quadrature amplitude modulation, QAM. While DMT is the system that manages the frequencies, QAM is the specific modulation technique used inside each individual DMT bin. Function: it changes both the amplitude, strength, and the phase, timing, of the carrier wave to represent a symbol containing multiple bits. Capacity: on a high-quality line, a single DMT bin can carry up to 15 bits per symbol using high-order QAM, example 32768 QAM. If the line is noisy, it might drop down to 2 bits, QPSK. Carrierless amplitude phase, CAP. CAP was the primary competitor to DMT in the early days of ADSL, mid-1990s. How it works: unlike DMT, which breaks the signal into hundreds of small pieces, CAP is a single carrier modulation. It treats the entire data frequency as one large block. Why it failed: while simpler and cheaper to build initially, CAP lacked the fine-tuned noise resistance of DMT. If interference hit one part of the frequency, the entire CAP signal could be disrupted. It is now considered obsolete in the DSL world. 2B1Q, 2 binary, 1 quaternary. This is an older line coding technique rather than a modern modulation in the sense of RF. It was the standard for IDSL and HDSL. Mechanism: it maps pairs of bits, 2 binary, to one of 4 voltage levels, 1 quaternary. Usage: it is still found in legacy ISDN lines but is rarely used in high-speed residential broadband today because it uses too much bandwidth at lower frequencies. Summary table: modulation by DSL type primary modulation system internal encoding ADSL/ADSL2 plus DMT, discrete multitone, QAM VDSL/VDSL2 DMT, discrete multitone, QAMG.fast DMT/OFDM QAM, up to 4096 QAM, HDSL2B1Q or CAP pulse amplitude modulation early ADSL CAP, carrierless amplitude phase, QAM like single carrier. Why DMT became dominant: the dominance of discrete multitone, DMT, over competing schemes like CAP, carrierless amplitude phase, was not just a result of a marketing battle, it was a victory of technical adaptability over simple design. In the early 1990s, the line code wars saw CAP as the early favorite due to its simplicity, but DMT eventually won the standardization battle and became the global foundation for ADSL, VDSL, and G.fast. Here is why DMT became the undisputed king of xDSL: superior fine-tuned noise resistance. The copper wires used for DSL are hostile environments. They are prone to interference from AM radio, fluorescent lights, and crosstalk from other lines. DMT's approach: by splitting the wire's bandwidth into hundreds of tiny subchannels, bins, DMT can treat each frequency independently. If a specific frequency is hit by a noise source, like a nearby radio station, the modem simply shuts down that specific bin and moves the data to a cleaner one. The CAP failure: since CAP treated the entire frequency as one giant block, a single strong noise spike could disrupt the entire signal, causing the connection to drop or lose massive amounts of data. Adaptive bit loading: the Swiss cheese strategy, DMT allows for a feature called bit loading. During the initial handshake, the modem measures the signal-to-noise ratio, SNR, for every single bin. High-quality bins: if a frequency is very clear, DMT might pack it with 15 bits of data, using high-order QAM. 0.5 low-quality bins: if a frequency is weak or noisy, it might only carry 2 bits. Result: this allows DMT to squeeze the absolute maximum capacity out of every individual copper line, regardless of its length or age. 0.6 CAP could only apply one average setting to the whole line, which was inherently less efficient. Rate adaptation and reach: DMT is naturally better at rate adaptive DSL, rad slow. 0.7 As you move further from the telephone exchange, high frequencies disappear first due to attenuation. DMT handles this gracefully by simply turning off the high-frequency bins and continuing to work on the lower ones. 0.8 This allowed DSL to reach customers much further away from the exchange than CAP-based systems could. Resistance to impulse noise: impulse noise consists of short, sharp bursts of interference, like a motor starting up. In CAP, a short burst could wipe out dozens of small, fast symbols in a row. 0.9 In DMT, the symbols are much longer in time, even though they are narrower in frequency. 0.10 This means a short burst of noise only affects a small fraction of a DMT symbol, making it much easier for forward error correction, FEC, to repair the damage. 0.11 The standardization and openness factor: DMT's victory was sealed by the ANSI T1.413 standard and later the ITU-TG .992.1, G.DMT, standard. Proprietary versus open: CAP was largely a proprietary technology championed by AT&T and Globespan. 0.12 DMT, meanwhile, was an open standard developed by a consortium, including Stanford University and Amati Communications. 0.13 Vendor choice: because it was an open standard, many hardware vendors, Huawei, Nokia, Cisco, could build DMT chips. 0.14 This drove down costs and ensured that different modems could talk to different DSLAMs, creating a healthy global market. Summary comparison: feature: CAP, single carrier; DMT, multi-carrier, good on clean lines, Poor on noisy, maximum efficiency through bit efficiency ones. Loading. Highly flexible, avoids dead flexibility, rigid, all or nothing approach. Frequencies. Standardization proprietary, at NT/Globespan. Global Open Standard, ITU/ANSI. Performance limited reach. Longer reach and higher speeds.